Hi, this is Shaheen.
And this is Arki.
And in this paper, we're introducing a framework for assembly planning that uses string diagrams as the unifying representation for design, planning, scheduling, and simulation.
String diagrams are a powerful mathematical and graphical calculus for reasoning and category theory, and there are already broad applications, for instance, in linguistics, requirements engineering, or computer science in general.
So today, design methodologies like design for assembly propose the design of products in such a way that their final assembly is faster, cheaper, and more efficient. However, implementing these methodologies is difficult because there is very little tool support. The main problem is connecting computer-aided design to off-the-shelf planners, schedulers, and simulation tools in a cohesive way.
And to demonstrate the capabilities of string diagrams to address these problems, we implemented our own framework called compositional planning and a simulation in Minecraft. So we start with a bunch of bricks like this, and in the end we want to come up with an assembly like this, for instance, of a house or a more complex model.
Our compositional planning pipeline consists of 4 steps. The first step is to infer a connectivity graph from a CAD model. The second step generates string diagrams from the connectivity graph. These string diagrams correspond to assembly plans for the CAD model. Since there are many possible string diagrams, we focus on 2 kinds of plans: sequential plans and parallel plans. The third step generates a schedule for a plan, defining an order for the operations that must be executed in the assembly process. The fourth step executes the schedule. We simulate the execution in Minecraft for visualization and for measuring its performance in terms of time to build. Before starting with the assembly planning, the assembly must be designed. In this case, we create an LDRAW model of the house. From the textual representation of the CAD model, we infer the corresponding connectivity graph. By topologically ordering the edges of the connectivity graph, we generate a sequential plan. For a fast assembly, we need to create a plan that allows for parallelism. To do so, we first identify sub-assemblies by applying the Louvain algorithm to the connectivity graph. The black boxes in a string diagram correspond to a partitioning of the connectivity graph, and the labels indicate the number of bricks per subplan. Finally, we derive schedules from the plans, which assign a definite order to the operations of the plans. The assembly process can be observed in the Minecraft-based simulation. The schedule and the number of available workers determine the time to build. The simulation of the assembly process with 16 workers and the parallel schedule is approximately 3 times faster than with the sequential schedule. The compositional planning framework can be used with different models as well. It can be easily extended for other domains and is not limited to the assembly of brick constructions.